All right, so just to review the formulas we've got so far, we have kinetic energy. Although usually what we really care most about is change in energy. So let's take a look at formulas for change. If you don't want change, if you want the actual amount of energy, just drop the delta. So what's our usual formula for change in kinetic energy?
One half mv squared.
Yeah. 1/2 times mass times velocity squared. Although if we want to delta,
or change in velocity squared.
Yeah, the velocity is presumably the only part of that that's going to be changing. We're assuming constant mass. So the velocity squared is the changing part. And those parentheses indicate that you should be squaring both the initial and final values first, and then subtracting v final squared minus v initial squared. And then we were dealing with potential energy of gravity last time. And what was our usual formula for that?
mgy.
Yeah. Mass times acceleration of gravity times height. And of those, what's the only thing we're expecting to change as an object moves?
Height?
Yeah, the height itself. So we'd have mg delta y. The idea is that if you have delta mgy, any constant multipliers can be pulled out of a delta, because what this indicates is final value minus initial value. But if mg is the same on both terms, you can factor that out. And you're left with y final minus y initial. In other words, delta y. So this really is a case where you can just factor out mg. And this is true for both sums and differences. If you have sum of a constant times a variable, the constant can be pulled out of the summation. If you have a difference of a constant times a variable, you can pull the constant out of the difference. So we just get mass times gravity times change in y. Acceleration of gravity can change if you're moving very far away from the planet's surface, but we're assuming we're staying close to the planet's surface the whole time. So we're treating g as a constant here. Any questions on that so far? And then we're also going to look at spring potential energy. And do you have a formula for that yet?
Yeah, it's 1/2 kx squared, or change in x squared.
Right. The spring potential energy itself would be 1/2 times spring constant times x squared. But again, if you apply a delta to both sides, you can pull the 1/2 k out of the delta because that's a constant. And you're left with just 1/2 k times the change in x squared. And what does x represent here?
The distance away from equilibrium.
Yeah, distance from equilibrium. If you have the spring at equilibrium, like if you've just got a spring and there's no forces on it, it's going to be some natural rest length. That distance is called, or that equilibrium location we're going to call 0. So if you just got like a spring attached to a wall and there's no forces acting on it, we're going to treat this location as x equals 0. If you then stretch out the spring, let's say you just grab this end and start pulling. If you stretch the spring to make it longer, you're going to be at a new location, which is going to be positive. So positive values for x suggest that we have stretched the spring, or alternatively, if you compress the spring, if you grab the spring and push on it to make it shorter, then that's going to be considered a negative value for x being less. So generally, positive x values means we have stretched the spring, negative x values means we have compressed the spring. But the thing is, since we're going to be squaring x anyway, what's going to happen to a positive or negative when you square it?
It becomes positive again.
So that means the spring potential energy is never going to be negative, regardless of whether you're stretching it or compressing it. Like if you take this spring and stretch it 3 centimeters, it takes a certain amount of work to do so. You're investing energy into the spring by stretching it out. On the other hand, if you compress the spring, you're also doing work. You're investing energy into it. And the idea of this x being squared means it doesn't matter if you're stretching or compressing. Pulling spring out 3 centimeters or pushing the spring in 3 centimeters takes the same amount of work. You've got complete symmetry, which you can also see graphically. If you made a graph of x versus potential energy, what would the graph of 1/2 kx squared look like?
It'd be a parabola.
You get a parabola, because it would be x squared. And specifically, where would the vertex of that parabola be?
At 0, when x is 0.
Yeah, we should expect the vertex at 0 because we don't have any other modifiers. If we had a plus something x or a plus some constant, that would move that around. But if it's just something x squared, the vertex is going to be at 0. And so we're going to get an upwards opening parabola with vertex at 0. And that parabola is completely symmetric across the potential energy axis. So if you stretch 3 centimeters, it takes a certain amount of energy to get to that location. If you compress the same 3 centimeters, it takes the same amount of energy to get to that location. So we've got complete symmetry. It doesn't really matter if you're stretching versus compressing. What if you had a different K value? Like let's say you had a stronger spring with a larger K value. How would that influence the graph? If you just made K a larger number.
It will make the parabola narrower.
I'd be careful
If
about.
that's the right way to describe it.
Yeah, I mean, it looks narrower, but I'd be careful about saying narrower because narrower kind of indicates it doesn't go as far out in the x direction. But this parabola can go as far out as you want. It's not like it just stops here. I would say a more accurate way to describe that would be to say it's steeper, that you're stretching it out vertically. You're not really compressing it horizontally, you're stretching it vertically. You're taking this parabola and stretching it upwards. So it would look something like this. And note that both of these parabolas are in theory at least infinitely wide. We're just stretching it in the vertical direction. So this would be a stronger spring. A larger K value, larger spring constant. Or if you made the spring weaker, if you made K value smaller, it's just going to take this and flatten it. So that would be small K value. So the strength of the spring, the value of K basically tells you how steep that parabola is, how stretched or compressed the graph is. And graphs like this can be really useful for figuring out information about how something behaves. The delta potential energy formulas, the whole idea of the energy interaction model, this has advantages and disadvantages. A delta only cares about what values. How do you usually calculate delta as something?
You do a change, right? You're like comparing the final and initial states of stuff.
Exactly. You're just comparing initial value and final value. Delta something is final minus initial. So the delta something, anything involving deltas, you're only looking at the initial values. You don't care about what happens in between. Sometimes that's an advantage because you don't have to know anything about what happens in between. But sometimes it can also be a disadvantage because it doesn't give you any information about what happens in between. So sometimes the delta approach is very useful. Other times it's useful to look at a graph of the type of energy involved because then you can see what actually happens in between. You can see what's going on at every location, not just two locations that you're comparing. So we're going to be looking at both approaches over the course of the quarter. Any questions on that so far? Also on this graph, where would you expect to find the lowest potential energy? Where is the potential energy at its minimum?
At the origin.
Yeah, at the origin. which is supposed to represent equilibrium for the spring. So equilibrium is the location where the potential energy is its lowest. And that's typically going to be true for equilibrium. Any equilibrium location is the location of lowest potential energy. If you move in either direction, like if you stretch the spring or compress the spring from equilibrium, you're increasing its energy. So that's why the indicator is X here. X, in fact, we often use the indicator for spring potential energy. We usually describe as absolute value of X. It doesn't matter whether you're stretching or compressing. If X is getting further from zero, you're increasing the spring potential energy. If X is getting closer to zero, you're decreasing the spring potential energy. Any questions on that so far?
I do have a question real quick.
Go ahead.
If we set the equilibrium position to be something other than zero, does that change the equation for delta potential energy?
Yeah, it's possible to set it up in a different way. If we, this version of the equation is treating equilibrium as zero. You can also rewrite the equation by using the length of the spring as the variable. If you go to spring, instead of using distance from equilibrium as the variable, we could use length of the spring as the variable. Like, let's call this length L. And specifically the equilibrium length, we're going to call L sub 0. So at L sub 0, when the length is L sub 0, it should have 0 potential energy. But if we stretch out the spring, it's now longer than equilibrium. So this distance we would call L. So L would be the length right now. And if we want to use the same sort of formula, the potential energy should still equal 1/2 times K times displacement squared. But we're going to have to write out the displacement differently if we want to write it in terms of L. The displacement is how much further it's stretched from equilibrium. So could you write this displacement in terms of L and L naught?
Yeah, it will be L minus L naught and then square that distance.
Yeah, if we just take that difference, L minus L naught, that's how much it's been stretched. So L minus L naught is how long it is right now minus the equilibrium length. So if we just replace X with L minus L naught, we get another formula for spring potential energy. And the order you subtract doesn't really matter because you're going to be squaring it anyway. But this is another way of writing out the formula for spring potential energy. Potential energy equals 1/2 times K times, and this is still how far it's been stretched or compressed. We're just writing it as length of the spring right now minus equilibrium length squared. So this is certainly another way you can write potential energy. I usually don't find this one as convenient because it's often kind of problematic if you're writing out delta. Like if you want to write out delta potential energy in this case, you'd have 1/2 times K times the final value minus the initial value. So final value of L minus L naught squared minus initial value of L minus L naught squared. And taking a difference of squared differences gets kind of confusing. So I usually just think of X as the variable in question, X representing the distance from equilibrium right now. Either way works, I just find this one more convenient to use. Any questions?
Perfect, thank you.
Could we also go over work? Because I feel like we haven't really touched on it just yet, but we're starting to get problems that are asking, how much work did this object?
One more thing on spring potential energy first. If we were graphing this instead, if we were graphing L versus potential energy instead of X versus potential energy, Let's take a quick look at what that graph would look like. If we were graphing L versus potential energy, and we wanted to graph potential energy equals 1/2 times K times L minus L naught squared. L naught is a constant. So if we're just subtracting a constant from the variable before we square it, what would that minus a constant do to the graph? If you just have the parabola, 1/2 kx squared, but then you subtract a constant, like if we were graphing x minus 5 squared, how would that influence the graph?
It would shift it, right?
Yeah, it's just going to shift it. And since we're specifically subtracting before we square it, that's going to shift it in the direction of L, specifically in the positive direction in this case. Like if you change L to L minus 5, then the L value 5 acts like what 0 acted like before. So L naught is going to be your new vertex. We're going to have a vertex at L naught and a parabola opening upwards from there. So if you're graphing length versus potential energy instead of displacement versus potential energy, it's going to be centered at equilibrium length rather than centered at 0. Still the same concept. We're basically just using a different coordinate system to graph the same type of energy. Any questions on that so far? And again, we're usually going to be using this formula, the 1/2 times K times change in displacement squared. But sometimes it is useful to be able to graph it in terms of length rather than in terms of displacement. So either way works, just whatever's more convenient in those circumstances. And let's talk about work also. Work is, what exactly is work? How do we define work in terms of physics? Like if I say
Force over a certain distance.
Yeah, work is defined as a force applied to an object as it moves some distance. And specifically, we calculate it as force times distance. How much force you apply, or how much force is being applied, whatever is applying it, times how far the object travels. And that's specifically the force applied to the moving object. So if you're pushing on an object but it's not moving, you're not actually doing work in the context of physics. If you push on the object while it's moving, you are doing work. And these force and distance have to be at least partly parallel. They can't be, if they're perpendicular, you're not actually doing any work. And that work represents a transfer of energy. Caused by a force on a moving object. So, and we usually call this a mechanical transfer of energy. As opposed to heat, which is also a transfer of energy, but heat is caused by a difference in temperature, whereas work is a transfer of energy caused by a force on a moving object. And specifically, the amount of force being applied to the object times how far it travels tells you the amount of work involved. Any questions on that so far? So for instance, if you know how much force is being applied and you know how far the object travels, you can multiply those to find how much energy was transferred as work. Or alternatively, if you know how much energy was transferred and you know how far the object moved, you could divide to figure out the force on the object. However, this force is really an average force, because the force might not be the same value the whole time. Sometimes it is. Like if you're lifting an object, you're applying a constant force to balance out the force of gravity. But if you're compressing a spring, the amount of force you get from the spring changes as the length of the spring changes. Like at equilibrium, you have to apply essentially no force at all. Once it's compressed, you have to apply a little bit of force. The more it's compressed, the more force you have to apply to balance out the force from the spring. So the force could actually be changing. More formally, the idea is we'd be adding up. We'd take like the force right now times a little bit of distance, times the new force, or plus the new force times a little bit more distance, plus the new force times a little bit more distance, plus the new force times a little bit more distance. In calculus, what tool do we use to add up a whole bunch of tiny changes? Yeah, integration. The work done is actually the integral of force dx. That is the amount of force time right now times a little tiny bit of distance evaluated from x initial to x final. That's really all an integral is. An integral is just adding up lots of infinitely tiny pieces. So the integral, that is adding together all the little bits of force times distance, is the total amount of work. You can approximate that with force times distance if you have some way of approximating the average force. But the exact value is integral of force with respect to distance. And this is often true with any quantity defined as integrals. Anytime you got a quantity defined as integral of some function dx or d whatever, you can always approximate that by taking the average value of that function times the change in d whatever. If you have the actual average, it's going to be exact. If you have just an approximation for average, you'll get an approximation of the integral. Any questions on that so far? So let's try applying this to a spring. Let's say you have a spring, and let's say its spring constant is 20 newtons per meter, which could also be written as joules per square meter. The reason for that is joules is the same as newtons times meters. So if you divide both sides by meters squared, on the left side, you get joules per square meter. On the right side, one of the meters cancels out, so you get newtons per meter. So those are just two different ways of writing the same units. And both of those are valid as ways to write the spring constant. So if that's the spring constant, and let's say it is compressed from equilibrium to 10 centimeters. How much work was done? So how could we calculate the amount of work there? If we know the spring constant, if we know how far it was compressed, how would we calculate the amount of work?
Sorry, could you
Would
repeat that
you-
one more time?
What was that?
Oh, could you repeat that one more time?
If we know how much the spring constant is, and we know it's compressed, the spring is being compressed from equilibrium and then compressed 20 centimeters beyond that. And we want to know how much work did that take? Because this takes effort, right? If you got a spring and you want to compress it, you're doing work to compress it. And this counts as potential energy because you're investing this work into it. And then like you could tie off the compressed spring and that is now stored energy. But how could we calculate how much work it took to do that? We want to know.
Convert the centimeters to meters.
What was that?
Would you divide the spring constant by the distance, or 20 over 10 centimeters, whatever that is in meters?
Well, the 20 newtons per meter, you could interpret this as saying, if you want to compress it to a certain distance, the amount of force you have to apply just to hold it at that distance is 20 newtons of force per meter of distance. But this doesn't mean we're actually dividing by distance to make further calculations. This is saying how much force it requires per meter that it's compressed. So if you want to compress it 1 meter and hold it there, you got to apply 20 newtons. Compressing it to 2 meters and holding it there would require twice that much, 40 newtons. And compressing it 3 meters would require 60 newtons of force. But that still doesn't tell us the amount of work. If we tried calculating work as force times distance, we could take the amount of force times the distance compressed, 10 centimeters, but we would need an average force. We can't just take the force at the beginning or the force at the end. Instead of using the definition of work, though, as force times distance, it's going to be much easier to use the idea that work is a transfer of energy. If you write this out as a conservation of energy setup, as you compress the spring, what types of energy are actually changing?
Potential energy of the spring is changing.
Yeah. If all you're doing is taking the spring from equilibrium length to compressed, and specifically if it's originally at x equals 0, and its final situation is compressed 10 centimeters, so we call that negative 10 centimeters, or negative 0.1 meters. So the spring starts off at equilibrium, so we'd say x initial is 0 meters. It ends compressed by 0.1 meters, so we'd say x final is negative 0.1 meters. So that means we know the potential energy of the spring is changing. And specifically, if we look at absolute value of x, we know x initial is 0 meters. X final is negative 0.1 meters. So is the absolute value of x increasing or decreasing here?
Increasing?
Should be increasing, right? Because we're going, I mean, 0 to negative is a decrease, but if we're looking at absolute value, the absolute value is increasing. And you can interpret that as getting further from equilibrium. In general, if you're getting further from equilibrium in either direction, you're increasing the potential energy. If you're getting closer to equilibrium from either direction, then you're decreasing the potential energy. We're getting further from equilibrium, so that's an increase in potential energy. Nothing else is changing. We're not really looking at anything getting faster or slower. We're not looking at anything moving up or down, so there's no gravitational potential energy, no temperature changes, no bond changes, phase changes, no chemical reactions. So this is the whole system. And would you treat that as an open system or a closed system?
Open, because you're doing work on it.
Yeah, the very fact that we're doing work on it suggests this is going to be an open system. Also, the fact that only one thing is changing and nothing else is changing in the other direction to balance it out means this has to be an open system. And you're doing work to it, so work is entering the system. We could then write out our conservation of energy equation. Generally, for any open system, delta E total should equal work plus heat. In this case, the only type of energy changing is spring potential energy, so that's delta E total. We've got work being done. We've got no heat at all, just work. And we can now fill in our formula for spring potential energy. 1/2 times K times delta X squared. And if our goal is to find out how much work was done, we don't really even need to fill in a formula for work. We just know work equals all this. If we can calculate this, that's the value of work. So we can now fill in those values. 1/2 times the spring constant times delta X squared. So that'll be X final squared. And do I need to worry about this negative here?
No, because we're squaring it.
Yeah, the very fact that we're going to be squaring it means we can just ignore that negative. So 0.1 meter squared minus the initial value, 0 squared, which is still 0, equals work. And we could then multiply that out. 1/2 times 20 would be 10. 0.1 is 1/10. Square that, you get 1/100th. And meters squared. 10 times 1/100th would be what?
1/10.
So we get 1/10. And then for the units, if we're combining newtons per meter times meters squared, what happens?
It's Newton meters, which is a joule.
Exactly. One of the meters cancels out. We're left with newtons times meters, which is the same as joules. So we can write this as 1/10 of a joule. In other words, compressing this spring 10 centimeters from equilibrium costs 1/10 of a joule worth of work. So that's the amount of work we need to do to make this happen. Any questions on that so far?
Can we see a vertical example of this?
Yeah, if it was vertical, what difference would that make?
You would have to take into account the mass being added on to the spring,
And not just
or it's just the spring.
Also, what other type of energy would be involved if it was vertical motion?
Gravitational.
Yeah. So let's try an example where you've got a vertical motion. So that's going to involve potential energy of gravity and potential energy of the spring. Let's say you're dropping an object off of a building. So you've got a brick that you're about to drop off the side of a building. And let's say you're dropping it from the height of the building, which is, let's say 20 meters above ground level. And let's say the brick has mass 5 kilograms. And let's say we're going to be dropping that onto a spring. And that spring is, let's say, originally 5 meters high. And let's say we also know the spring constant. Let's say the spring constant is 1,000. Is it too much? Let's say just 200. And let's say 300. So the spring constant is 300 newtons per meter, which means it would take 300 newtons of force to compress it each meter. And what we're going to do is we're going to drop the block, or drop the brick, and what would you expect to happen to this brick?
It will gain kinetic energy.
Right. As it falls, it's losing potential energy, gaining kinetic energy, so it's going to get faster and faster and faster until what happens?
Until it hits the spring, right?
Yeah. As soon as it hits the spring, it starts losing kinetic energy, and that lost kinetic energy turns into what?
The spring potential energy.
Right. Once it hits the spring, the kinetic energy starts transitioning to spring potential energy. So the object slows down as it compresses the spring. Eventually, it's going to slow down enough to come to a stop. And after that, it might bounce back up again. But let's say we want to know how much does it compress the spring at most. We want to find the maximum compression of the spring, which means how much does the spring compress at the instant when the object comes to a stop. So this will be our initial situation. And our final situation is going to be the spring has been compressed And the brick is now as low as it can possibly be. Any questions on that so far? In terms of initial and final setup? So what types of energy are changing from initial to final? Or what indicators are changing that tell us about some sort of energy? Yeah, the height's changing. We've got an initial height, and we've got a final height that's different. So since height is changing, and specifically is height increasing or decreasing? Yeah, the object has moved down. The final height is lower than the initial height. Y has decreased. So that means potential energy of gravity has decreased. And we can list out initial and final values later. What other type of energy is changing from initial to final? Velocity. What's the initial velocity? How fast is the brick moving at the instant you release it? Yeah, starts off moving at speed 0 meters per second. What about the final velocity? How fast is it moving at the instant the spring reaches maximum compression?
0.
Also 0. We're assuming we're waiting for the mass to come to a complete stop, because that's when the spring is going to be most compressed. So how much has the speed changed? Has the speed increased or decreased overall?
No change.
Yeah, overall there's no change. Even though there's changes in kinetic energy in between initial and final, it's getting faster and faster and faster, then slower and slower really quickly. The initial and final values are the same. So overall, the delta kinetic energy is 0. Initial speed equals final speed. So delta KE is 0. And that actually tells us we can ignore kinetic energy in this problem. If we cared about what happened in between, like if we wanted to know how fast is it going at the moment it impacts the spring, then that would matter. But if we just care about this initial and this final, overall there is no change in kinetic energy because we return to the same speed that we started at. So we can leave kinetic energy out of our diagram. But what else is changing? What other type of energy is changing from initial to final?
The spring?
Yeah, since we're going from a spring that's not compressed to a spring that is compressed, we're changing the compression of the spring. So spring potential energy is changing. And since we're going from equilibrium to not at equilibrium, is that an increase or decrease in spring potential energy?
Increase.
Yeah, that should be an increase. Anytime you're moving away from equilibrium, that's an increase in potential energy. If you were moving towards equilibrium, if you were going from compressed back towards uncompressed, that would be a decrease. And so we're going to describe this in terms of the absolute value of x, x being the compression. So x here doesn't mean horizontal motion. X in this context means how compressed the spring is. We are gaining compression, so that's an increase in spring potential energy. We can even write out initial value at least. At the beginning, how much is the spring compressed?
Zero.
Yeah, it's not compressed at all to begin with. And keep in mind, that's not the 5 meter length. 5 meters is the length of the spring, but the compression, the x value is how far is it from equilibrium. At the beginning, it's at equilibrium, so its initial x value would just be 0. Do we know how compressed it is in the final situation? That's still unknown, right? We don't know how much. I mean, that's what we're trying to find out. We want to know how much does it compress the spring. So x final is unknown. What about y values? Do we know a starting height and or an ending height? We don't know either one? How?
Starting height would be 20.
Yeah, we know it starts off, well, at least we know it starts off at the top of the building, which is 20 meters tall. And the thing is, there's some flexibility in how you choose the coordinate system. We could say ground level is 0 and the starting height is 20. Or we could say the starting height is 0 and ground level is -20. So you can choose whatever point you want to call y equals 0. I think, though, it probably would be convenient to call ground level y equals 0 here. So let's go ahead and say ground level is y equals 0. Then the initial y value is 20 meters. But we don't know the height at the end. And I think those are the only types of energy that are changing here. There's no overall speed change. We're assuming no temperature change, no phase change, no chemical reactions. Should we treat this as an open system or a closed system?
A closed system?
Yeah, I think a closed system makes sense here. There's no heat transfer, probably no work done. Is there any circumstance where you would expect work to be done here, where you would expect this to be an open system? Is there any other force that could be doing work on the brick as it falls?
Air friction?
Yeah, if you had some sort of air resistance going on, we would treat that as work leaving the system. But in this case, a brick is very massive and very compact. It's very tightly clustered mass. So I would treat that as air resistance is probably negligible. So I think we can reasonably treat this as a closed system, which means these changes are going to have to add up to what? If it's a closed system, the changes in energy add up to, yeah, those got to add up to 0. We could now fill in some formulas. Gravitational potential energy is our usual mg delta y. Spring potential energy, 1/2 k delta x squared. And if we start filling in some values, I wouldn't necessarily fill in the numbers yet, but some of these values are zeros. So I'm going to write out m times g times y final we don't know. Y initial we do know. In fact, let's just call that h. So h is just the height of the building. That's 20 meters. Plus 1/2 times k times an unknown x final squared minus, we at least know it starts off uncompressed, so we can go ahead and fill in 0 for x initial. Technically 0 squared, but it's still 0. So mg times y final minus h plus k/2 times x final squared must equal 0. Problem is, how many unknowns do we have here?
2.
Yeah, we've got 2 unknowns. We don't know the final height of the brick above ground level, and we don't know the final compression of the spring. And one equation with 2 unknowns isn't very useful. We want to have one more fact about how these x final and y final are related. But we can actually get that with some geometry. If y final is the final height above ground level, and x final, what is x final supposed to represent? What does x mean in the context of a spring potential energy equation?
It's how much it compressed compared to equilibrium.
Yeah, exactly how much it's compressed from equilibrium. So if we compare the height right now to the equilibrium height, This difference is x final. So x final is how far it is from equilibrium to where it is right now. And what do you notice about x final and y final?
So
They add up
Wi-Fi.
to 5 meters.
Yeah, x final and y final have to add up to 5 meters. So we could write that out. We could write that as an equation. We can say x final plus y final must add up to 5 meters. And we can now use that as our second equation. We now effectively have a system of equations. An equation with two unknowns, x final and y final, and another equation with those same two unknowns. So if, for instance, you solve for y final here, you get y final equals what?
Five minus x final.
And you can now use that to substitute everywhere you see y final in the conservation of energy equation. So if you just replace y final with 5 minus x final minus the height, and what was the height of the building?
$20 meters.
So we fill in 20 meters there, times m times g, that's 5 kilograms times, and what are we using for g here?
10.
Yeah. Gravity on Earth is 9.8 meters per second squared, but let's round that off to 10. So 5 kilograms, the mass of the brick, times 10, the acceleration of gravity, times x or y final, which we're writing in terms of x final, minus the height, y initial, plus k over 2. And what was k here? The spring constant originally was what?
300.
Yeah, so 300 over 2 times x final squared equals 0. And simplifying this a bit, we've got a 50 times, actually we could simplify this first. 5 minus 20 would be negative 15 minus x final. Those both get multiplied by 50. So we've got a negative 50 x final. 50 times 15 would be negative 750. Then 300 over 2 would be 150. So we now have an equation with a constant term, an x final term, and an x final squared term. What could you use to solve an equation like that?
Factoring.
Yeah, this is a quadratic equation, so you can solve it using the quadratic formula. You might want to simplify it first by dividing both sides by 50, because all of these numbers are multiples of 50. Divide both sides by 50 to make the numbers easier to work with. Apply the quadratic formula, and that should give you a value for x final. Then you could plug that in here and find what y final is going to be. Any questions on that? All right, so try working out the rest of the algebra on your own. See if the result you get makes sense in terms of what you'd expect for compression. And I'll see you next week.
You see?